Good day, everyone. My name is Raven Elijah C. Today, I will be presenting BJT, FET, and its AC and DC analysis, along with its frequency responses and operational amplifiers. So, I will be presenting. Okay. So, BJT, AC and DC analysis, FET, AC, DC. Frequency responses for both AC and DC, finally, operational amplifiers. So we will be starting off with what is a BJT. So a BJT or bipolar junction transistor is an electronic switch or an amplifier. At its core, it is a three-layer semiconductor sandwiched made of emitter, base, and collector sections. These are their terminals, collector, base, and emitter. So by feeding a tiny current into the middle layer or the base, we can control how much larger current flowing between the emitter and the collector. Essentially, it is like an electronic valve. So BJT comes in two types or two flavors, depending on those layers are stacked. So we have NPN type transistor. A P-type layer is sandwiched between two N-type layers. Current flows into the base to turn it on, and then the main current flows from collector to emitter. And then the other type is the PNP, which is the exact opposite. An N-type layer is sitting between the two P-type layers. Here, current flows out of the base to turn it on. The easiest way to tell them apart is the arrows. The NPN type is the arrow is pointing towards the emitter, and on the PNP, the arrow is pointing towards the base. Okay, so let's talk about the regions of operation there. So the region of operation is in this output characteristic curve of a BJT. We have the active region, saturation region, and the cutoff region. Depending on how we apply voltages to these terminals or junctions, the BJT operates in three main different regions: the active, saturation, and cutoff. So what is the cutoff region? The transistor is fully off. It will act like an open switch with zero current passing through. Like I said before, the current passing through collector to emitter is based on the current going to the base. So if we're going to use cutoff region, there is no current at the base. Okay. Next, the saturation region. The transistor is fully on. It will act like a closed switch, allowing maximum current to flow. Then finally, in the active region, this is where the magic happens for amplification. So the transistor is partially open, meaning changes in the tiny base current create large proportional changes to the collector current. Mastering these states is how we use BJT to either process digital signals or amplify audio and radio waves. So like I said before, based on how we apply voltages at the terminals, we can see that the x coordinate is the VCE voltage of collector to emitter, and the y-axis is the current, collector current here. Next. So we will talk about the DC analysis of BJT. DC analysis focuses on establishing the transistor operating conditions before an AC signal is applied. Biasing is the process of setting fixed DC voltages and currents at the transistor junctions. The DC load line represents all possible operating states of the transistor for a specific circuit configuration, drawn from the maximum saturation current, this part, to the maximum cutoff voltage, this part. The intersection of our bias currents and voltages on this line establishes the Q point or quiescent point for linear amplification. The Q point must be positioned in the center here of the active region on the load line to allow maximum unclipped signal swing. Because if we don't place our Q point at the middle, as you can see here, there's a possibility that the output waveform will be clipped that will result into distortion. Okay. So for the amplification mode of a BJT, we will talk about the common biasing configuration. There are three primary circuit topologies used to establish this bias point. First is the fixed bias. What is the fixed bias? This configuration will use a single resistor connected directly from supply. VCC is the supply to the base or B. While simple, it is very highly dependent on the transistor current gain because each transistor has their own gain. Because beta or gain varies wildly between individual components and changes with temperature. The Q point is highly unstable. The next common biasing configuration is emitter bias. Here, the emitter bias, this setup adds a resistor to the emitter terminal. The voltage drop across this resistor provides negative feedback. If collector current increases, current here, the emitter voltage increases, stabilizing the current. Lastly, our voltage divider bias. So what is the voltage divider? From the word itself, there is a voltage divider in the circuit. We have R1, R2. This is the most widely used configuration. It uses two transistors to form a voltage divider at the base terminal, making the base voltage fixed and independent of the transistor's internal parameters. It will offer the highest Q point stability against variation in gain. Because by temperature, BJT can vary its gain by its temperature. So after discussing all these common biasing configuration, you have their own perspective formulas for each configuration written, illustrated here. So we can derive these formulas by applying KVL in the base and the output. So since the writers of the book of electronics devices and circuit theory have already done that for us, we can just simply use their derived formulas here. Okay. Now let's talk about the stability considerations. Stability is critical because Semiconductor parameters are temperature dependent. Like I said, the BJT are temperature dependent. As temperature rises, the leakage current ICBO and beta increases. Without proper stabilization, these changes cause the collector current to drift upward, shifting. This is the collector current drift upward, shifting the Q point along the load line toward the saturation region. So if the collector current will be shifted upward, the Q point will also go upward. And in severe cases, this will lead to thermal runaway, which can destroy the device. Selecting a topology like voltage divider bias mitigates these effects by keeping the Q point fixed regardless of the thermal changes. So that's the advantage of using the voltage divider bias. So I will not be talking about each and individual formula used in BJT bias, but these are the most significant formulas that will be used that can be encountered in electronic devices and circuits problems in DC biasing BJT. In general, VB is 0.7, IC is equal to approximately equal to IE, and IC is equal to beta IB. Then we have the formulas as I said before. The fixed bias, IB is equal to VCC minus VBE over RB, and then the VCE here, and IC saturation region, VCC over RC, and then the other bias, emitter stabilized. Then this is the formulas, IB, RI, VCE, and then ISAT, ICSAT. And then next, another DC bias is the voltage divider bias. We have the getting the exact uh, parameters or values. We have two different sets of formulas. We get the RTH, IB, VCE, and then we have the approximate as well for a computing for the parameters. VB or VE, IE, IC, yeah, and then the other as well. These are all the formulas, very significant formulas that can be encountered. So next, we will talk about what I said before about the difference of the exact and approximate. What's the difference of that computing the parameters of the exact and approximate of a voltage divider bias? So we have a example for problem solving in the DC BGT analysis. The problem is determine the DC bias voltage VCE. So we will you will try to find the VCE voltage difference, potential difference of the terminal at C, collector, and the terminal at E. We will look for that. And the current IC for the voltage divider configuration figure 4.35. We will try to find the IC current going along through here. Okay? So we have the circuit, voltage divider circuit. So as I've said before, the computing the RTH, Thevenin equivalent, we have we will use the parallel R1 paralleled by R2. We will compute product over sum. Therefore, we will get 3.55 kilo ohms for RTH. Then the ETH, this is the formula. VCC times R2 over R1 plus R2. We just plug that in the formula. VCC is 22 and R2 39 and R1 R2. Then we will get 2 volts. Next, IB. So we follow the formula. ETH minus VBE. VBE is 0.7 here. See? Next. And then we apply the values we have obtained. The RTH, the RE is resistor at the emitter, which is 1.5. So we will just apply that. So ETH is 2 volts here. And then 0.7 VBE, RTH, and then plus 1, beta plus 1, RE, which is 1.5. Then we compute for the IB, 8.38 microamps. And then finally, we get to compute the IC. Remember that IC is equal to beta IB. So we multiply IB with beta. Beta is written given here, 100. So we multiply IB times 100 because we will get the IC, which is 8.4 milliamperes. This is the exact analysis. So we get the IC and we got the VCE. We will compute for the VCE. Going back to the formulas, list of formulas, VCE is, where is it? VCE is VCC minus IC, open parenthesis, RC plus RE. So we just apply that formula, VCC minus IC, RC plus RE. So we apply from the given, and then we will compute for the VCE. We have 12.34 volts. That's the exact solution for voltage divider. Then the other one is the approximate solution. So the approximate solution is that we will get VTH. The formula of VTH is equal to, is the same as getting the ETH, VCC times R2 over R1 plus R2. We apply the values, and then we will get 2 volts. And then we can get use this formula, VTH minus VBE, which is 0.7, and then RE. We apply it, we have IE. We now have IE. Next, the VCC, same formula as the exact. However, IC, since this is an approximate formula for approximate solution, is that we will use IC as IE. Since based here, IC is approximately equal to IE. So we're going to use IC as IE. So we just substitute what we have obtained for IE and then apply the values, and we will have this value. So as we can see, the differences of what we have achieved, it's very close to the exact 12.34 for the approximate 12.03. For IC, 0.84, 0.67. Very close. So in practical applications, in real life application, in the industry, uh, people really do not use the exact. We just use the approximate. On the condition of beta RE is equal to or greater than 10 R2. Okay? Next, we will talk about the AC analysis of BJT. So, while DC analysis sets the static operating point, AC analysis examines how BJT processes time varying signals. Under small signal operation, the input AC voltage is kept small enough, typically a few millivolt, so the transistor operates linearly around its fixed Q point. This prevents the output signal from distorting. Okay. So to analyze AC, to analyze the circuit's AC performance, we will replace the transistor with its AC equivalent circuit. So we have, for example, a fixed bias configuration. So you'll transpose or convert it into its AC equivalent circuit. This is the AC equivalent circuit. The arrow will pointing the all the DC source will be grounded, and then the arrow will be pointing to the ground. This is the ground. And then we will have H sub IE from the transistor, and also 1 over HOE also from the transistor. And then since this is the ground, this is the ground, we will flip this RC as the ground here. And then since this is connected to the output, this is the output, this is the output. Then this is the input here. This is the input. Such as the RE or hybrid model, in this state, all DC voltages are replaced with a ground, and all coupling and bypass capacitors are treated as short circuits. Okay. From this equivalent model, we we calculate four critical performance parameters: voltage gain, AV, and current gain, AI. The ratios of output voltage and current to their respective input values, defining the amplification factor. Input impedance, ZI, and output impedance. So, since they are all parallel, you will compute for its this will be the input impedance. And then for the output impedance, we will just be computing it in parallel. Next, the effective opposition the circuit offers to the AC signal source at input and to the load at output. Matching these impedances is essential. Matching these impedances is essential for maximum power transfer and signal integrity. So, there are three primary ways to configure a BJT, determined by which terminal determined by which terminal is shared between the input and output loops. So, the first is CE, common emitter. The input is applied to the base and the output is taken from the collector. It provides high voltage and current gain along with 180 phase inversion, making it most widely used configuration for general amplification. And then the common base, the input is at the emitter and the output is at the collector. It offers a voltage gain but a current gain of less than 1 because of its low input impedance and high frequency response. It is primarily used in RF applications. And lastly, the common collector, CC, is known as the emitter follower. The input is at the base and the output is at the emitter. It provides unity voltage gain and high current gain, high input impedance and low input impedance, making it it ideal for impedance matching and buffering. Yeah, here. Like I said, we have amplifier configurations, common emitter, input is applied to the base, and the output is taken from the collector. It provides high voltage gain. Next, the common base. Input is applied at the emitter, and output is at the collector. It offers high voltage gain, but a current gain of less than 1. Next, common collector, also known as emitter follower. The input is at the base, and the output is at the emitter. So we can, in this table, we can clearly see the differences of the input resistance, output resistance, voltage gain, and current gain, and finally, power gain, and its shifts in the phase. Next. So, in the BJT analysis, there's ton of formulas will be used. These are all the significant formulas that will be used in AC analysis of a BJT in electronic circuit devices. So we have RE, 26 millivolts over IE. Then we also have fixed bias here, voltage divider, emitter bias, emitter follower, common base, common collector feedback, and other stuff. These are all the significant formulas that used in BJT AC analysis. So let's try to solve one problem solving in AC BJT analysis. So you have this problem. Determine the AV1, AV2, AVT, and VO. So as we can see, this is a two-stage voltage divider. So first, we will start in DC. So determining AV1, AV, we have the formula AV is equal to negative RC over RE. Here, negative RC over RE. So how do we get RC? It is already there. RC is 2.2 kilo ohms. How do we get RE? RE is 26 millivolts over IE. Okay. So we need IE to get the RE, small RE. So how do we get IE? We simply use approximate solution like we did before. VTH is equal to VCC. Then we apply the values. 20, this is the VCC. 20, R2, this is the R2. Then apply, we get VTH 4.77 volts. Okay. Next, we get the IE. The IE, like the previous slides, IE is this is the formula of IE. IE is equal to VTH minus VBE over RE. VBE is equal to zero point 0.7. So IE is equal to VTH zero point 0.7 minus 0.7 RE. We apply the values, then we compute in our calculator. 4.07 milliamps. Then we get the RE. Since this is a two-stage, as we can observe that all of its parameters or values of its components is that they have the same values. 15 kilo ohms for the R1, 4.7, 4.7, R2, 2.2, 2.2, RC, 1 kilo, 1 kilo for RE. They are the same for the both voltage divider. Therefore, RE is equal to RE2. RE1 is equal to RE2. So we'll get the RE formula, 26 millivolts over IE. So we just apply what we have obtained for IE. Then we calculate. Therefore, 6.39 ohms is our RE for RE1, RE2. Small RE1 and RE2. Next. So we will get Z, input impedance. So as we have learned before, we can convert this into an AC equivalent. We'll flip the RB here, R1, R2, and the beta RE from the BJT, and then we will simply compute for its parallel resistance, R1, R2, and beta RE. We apply the formula, and then we type it in our calculator, and then we will have our input impedance. Since they are the same values, the input impedance for the stage 1 is also the input impedance for stage 2, 941.7 ohms. So next, we find the AV. The formula for AV is RC parallel RL over RE. So we have RC. RC is 2.2 kilo ohms. And then Z input. So the Z input impedance is 900, what we have obtained before. And then we get to compute the AV. 103.2. And the AV2, RC2 is equals to 2.2 over RE2, same as RE1. We have 344.29. So we ask ourselves, why is it that there's a difference in the formula for AV1 and AV2? Because since this is connected, all of this is connected, the output impedance of AV1 is connected to the input impedance of the stage 2. Meaning, the impedance of the stage 1, output impedance of the stage 1 will be cascaded with the input impedance of stage 2. Therefore, we will include the input impedance of the stage 2 here. That's why there's a difference of the formula in AV1 and AV2. Okay? So, how do we get the total AV or the gain? So, the total gain is simply multiplying AV1 and AV2. If you apply the values, then we get this. Then the VO is equal to V in times AV total. We apply the values, then we have our 0.89 volts output voltage. Next. Now, we will talk about the FET field effect transistor AC and DC analysis. Okay. What is a FET or field effect transistor? So, it is a three-terminal semiconductor devices for switching and amplification. Unlike BJT, which is a current controlled device, a FET is a voltage controlled device. Okay? It will operate by using an electric field. establishing by a voltage applied to the gate terminal. The gate terminal. So for BJT, current is applied at the gate or base, but for FET, it is by voltage because the control gate is insulated or reversed bias. The input current is negligible using an extremely high input impedance. Next. So, what are the types of FET? We have the JFET and MOSFET. What's the difference? What are they? What are those? FET are broadly categorized into two primary types based on their structural construction. What is the JFET? JFET, they are the conjunction field effect transistor. Junction field effect transistor. In a JFET, these are the JFET. The gate structure forms a physical PN junction with the channel operating exclusively in the depletion mode. Applying a reverse bias voltage to the gate widens the depletion region, narrowing the channel and restricting carrier flow until the channel pinches off completely. Next, MOSFET. What is a MOSFET? Metal oxide semiconductor field effect transistor. In a MOSFET, the gate is completely insulated from the channel by a thin layer of silicon dioxide. MOSFETs can operate in a depletion mode or much more commonly enhancement mode. In enhancement mode MOSFET, no physical channel exists until a sufficient gate to source voltage VGS exceeds the threshold voltage VTH, creating an inversion layer to permit conduction. So what are those? So what is the basically the difference of a BJT and an FET? So they are both transistors. One is current controlled, one is voltage controlled. So when choosing between BJT and FET, the fundamental distinctions lie in charge carrier mechanics and input dynamics. The BJT relies on both majority and minority carriers, making it highly sensitive to temperature and prone to thermal runaway. In contrast, FET is a unipolar device relying on only one type of charge carrier. This structural difference yields a negative temperature coefficient, preventing thermal runaway. Furthermore, while BJT require continuous base input current to remain active, FET only require voltage set up across their massive input impedance, making them far more power efficient in digital switching and integrated circuit devices. So let's talk about the DC analysis of an FET. DC analysis of a FET establishes the static operating currents and voltages before an AC signal is introduced. Unlike the linear relationships found in BJTs, the relationship between input voltage and output current in a FET is nonlinear. Okay. For JFET, and depletion mode MOSFETs, this relationship is defined by Shockley's equation. This is the Shockley's equation, where IDSS is the saturation drain current at VGS equals 0 and VP is the pinch off voltage. For enhancement type MOSFETs, which require a channel to be induced, we use the MOSFET square law operation. Square law equation. ID is equal to K meaning the temperature, conduction parameter is the threshold voltage, parenthesis VGS minus VT quantity squared, where K is the conduction parameter and VTH is the threshold voltage. VT is the threshold voltage. Both mathematical expressions demonstrate that drain current ID is a function of the square of the input voltage. Next. So let's talk about biasing methods and operating point. To achieve to achieve stable operation, we must select an appropriate biasing network to lock in the operating point or Q point. IDQ or IDQ and VDSQ. The primary biasing methods used almost the same as the BJT biasing. So we have the gate bias, self-bias, and voltage divider bias. Uses, let's talk about the fixed bias. Fixed bias or gate bias. It uses a separate DC voltage source to set VGS. This is the separate DC voltage to set VGS. While simple, it requires two separate power supplies and lacks self-stabilization. Okay, next, self-bias. Uses a transistor connected to the source terminal. RS. As drain current flows through RS, it elevates the source potential, creating a negative VGS relative to the gate without requiring an extra power supply compared to the gate bias. There's no extra power supply. Finally, voltage divider bias uses a resistive network at the gate terminal combining with a source resistor. This provides a highly stable Q point, particularly for enhancement type MOSFETs by fixing the gate voltage. Now let's talk about the DC load line. DC load line is derived by applying Kirchhoff's voltage law to the output drain source loop of of the of the circuit. The equation for the DC load line is this. Plotting this linear equation into the nonlinear FET drain characteristic curves gives us a visual representation of all possible operating states. The exact point where the bias equation intersects this load line establishes our Q point. Proper For proper linear amplification, this Q point must be fixed safely inside the saturation region of FET, preventing the device from drifting into off-mic or cut-off region. Just like the BJT, we do not want to let our cue point close to the ohmic region or the cut-off region to avoid distortion. So determining a proper cue point is by determining the ID and the VP. VGS and the VGS by applying whatever biasing methods we need and the proper power supply and resistors in our FET circuit. So these are all the significant formulas for solving FET circuits, FET transistors, and FET biasing. So we have the Shockley's equation, ID is equal to IDSS, 1 minus VGS over VP squared. And the other significant equations. For the biasing, we have the fixed bias, self-bias, voltage divider bias, and the other biasing methods, common gate configuration. These are all the significant equations that may be used to solve FET DC biasing in electronic devices and circuits. Next, we'll try to solve a DC FET analysis. So we have this problem for the network 7.85. Determine determine VG, IDQ, and VGSQ, VD, and VS, and VDSQ based on this circuit. So we have our VG. This is our formula for the VG. VDD, which is 20. VDD is equivalent of VCC in BJT. So VDD R2 over R1 plus R2. We apply the formula. This is what we get. And then based on the graphical solution, we will go into a process of if for ifs. So if VGS is equal to 0, we will apply ID is equal to IDSS. That is the first point, point 1. So if VGS is equal to 0, IDSS equals to ID. That's 10 millimeters. Therefore, in our graph, we'll put one first point in the 10 millimeters. Then the second, if VGS is equal to VP, then negative 3.5 volts, ID is equal to 0. Okay. So that will be our second point. We will apply VP is equal to negative 3.5 volts. We apply here negative 3.5 volts as our VGS. Next, VGS is equal to VP over 2. We get our VP. VP is this divided by 2. That's 1.75. And then our ID is equal to 2.5 milliamps. So we plot that in our graph, negative 1.7 and 2.5 milli. So negative 1.7 here, that this, and 2.5 milli. That's the third point. And the next point is VGS equal to 0.3 VP, negative 1.05 volts. ID is equal to 5 millivolts. So we compute and then we plot negative 1.05 and 5 milli. 1.05, 5 milli. That's our fourth point. So we now have 1, 2, 3, 4 points. We sketch a line along these points there. And then we calculate next for our VGSQ, our Q point. So our VGSQ is 2.61. This is VG. VG minus ID. Quantity 1 kilo ohms. And then ID, for our ID equal to 0. VGSQ is equal to 2.16. VGSQ is equal to VG is equal to 2.16 volts, and then VGSQ is equal to 0 volts. Then ID dividing our 2.16 over 1.1 kilo, we will get 1.96 here. So we point 2 2.16 and ID around 2 because that's 1.96 milli. We use a ruler against point 2, this point and 2 point. We will project a ruler pointing at the curve. Eventually, we will get a point in the curve which will represent a IQ, IDQ, quiz Q point, 3.3 milliamps, approximately 3.3 milliamps. And then for the VGS, we will get one around approximately 1.5 volts. So that will be our answer. Next, VD. We get VD. So we have VG, where they have ID, Q, VGSQ. Then we will find VD and VS. How do we get VD? We apply formula. VDD minus IDQ times RD. We apply the values we have obtained. We get 12.74 volts. Then how do we get VS? We apply formula ISRS equals IDRS. So apply formula, we get 3.63 volts. And finally, VDSQ, VDD minus IDQ, RD plus RS. We apply the values, then we get our answer. So where do we get our all these formulas? All these formulas is found here. Voltage divider, VDVS, voltage divider. It is all found here. You just have to look for it. Next. Okay. Frequency response. Oh, wait. AC analysis. Now we have AC analysis of FET. So we will talk about small signal, model AC equivalent circuit, gain calculation, input and output impedance, common source, common drain, common gate amplifier. So AC analysis of a field effect transistor evaluates how the device amplifies time varying signals under small signal conditions. The AC input voltage variation is kept small enough that the transistor operates around its estimated DC Q point, preventing signal distortion. So let's talk about the small signal FET model and AC equivalent circuit. To analyze performance, FET is replaced by small signal AC equivalent model. In this model, all DC voltages sources are shorted to the ground, just like the BJT AC equivalent model. The all coupling and bypass capacitors act as a short circuits for AC signals only. The core parameter of the FET model is transconductance, which is GM. This is the formula of GM, delta ID over delta VGS, which relates the input voltage variation to the output current variation. Then we calculate the fundamental parameters. Voltage gain, AV, it is the ratio of output AC input voltage to input AC voltage because the gate draws virtually no current. Current gain, AI, is mathematically as infinite. Next, input impedance. The resistance between seen by the AC signal source looking into the amplifier due to the insulated or reverse bias gate. ZI is exceptionally high. Lastly, the output impedance. The internal resistance of the amplifier circuit as seen from the output terminals looking back inward. Now let's talk about the amplifier configurations. There are three primary amplifier topologies, character categorized by which terminal is common to both input and output AC networks. So let's talk about common source. The common source, the input signals applied to the gate and output intake is taken from the drain. And high input impedance accompanied by 180 phase inversion between input and output. It is the most widely used FET amplifier. Next, common drain, also known as a source follower. The input is at the gate still, and the output is taken from the source. It features a voltage gain of less than unity, no phase inversion, extremely high input impedance, and very low output impedance, making it ideal for impedance matching and buffering. Then lastly, the common gate. The common gate input is applied to the source and the output is taken from the drain. With the gate connected directly to AC ground, it offers the voltage gain without phase inversion, but as low input impedance, making it highly suitable for high frequency RF applications where matching low impedance and coaxial cables is required. So these are all the formulas that can be used in AC analysis of FET amplifiers. You have the GM equals to delta ID over VGS. You have the GMO 2 times IDSS absolute of VP. GM is equal to GMO 1 minus VGS over VP. And then can also be computed as GMO multiplied by root of ID over IDSS. Then RD 1 over YOS equals to delta VDS over ID when VGS is constant. Then we also have the DC biasing, fixed bias. We have the input impedance, output impedance, and the gain. We also have the self bias, bypassed RS. We have input impedance, output impedance, and the gain. We also have self bias that is unbypassed RS, input impedance, output impedance. Then finally the voltage divider, input, output, input, output, and source follower, and all the other significant equations that will be used in FET amplifiers for AC analysis in electronic devices and circuits. So we will have to solve a DC, AC, sorry. This is AC of FET analysis. Determine the ZI, ZO, and AV for the network of figure 8.3 if GFS is equal to 3000 ms and GOS equals to 50 ms. Okay, so we have the circuit given here. VDD is 12 volts and the other resistors is stated here. Drain to source and gate resistors. And GM, you simply use GM is equal to YFS, 3 millisec, 3 ms Siemens. And then RD, 1 over YOS. Basically, we apply our value, 20 kilo ohms RD for the RD. And then we get the ZI input impedance, basically the RG, which is 10 mega ohms. Then for the ZO, RD is parallel to 20 and 3.3 kilo ohms. So we get 2.83 kilo ohms. Finally, the AV, applying the formula. We have GM, which is what we have here, 3 millisiemens. And what we have here, 2.83 kilo ohms for the output impedance. So that will be our answer. AV is equal to negative 8.49 gain. Next, we will talk about the frequency responses of AC and DC of BJT and FET. So first, let's introduce frequency response. What is frequency response? The frequency response of an amplifier is a measure of its ability to maintain a stable output level across the range of signal frequencies. In ideal analysis, we assume amplifiers treat all input signals equally regardless of frequency. In practice, an amplifier's voltage gain varies significantly depending on the frequency of the incoming AC signal. Analyzing this relationship is critical because electronic systems must process complex signals such as audio, video, or data streams that consist multiple frequencies combined together. If an amplifier cannot handle the entire frequency spectrum of an input signal, uniformity distortion occurs. So let's talk about the frequency spectrum concept. To understand the frequency response, we must we must look at the frequency spectrum. Any complex or real-world signal is composed of a collection of sine waves. Everything we hear, we see, or what we feel, basically they are all vibrations, and basically they are all sine waves of different frequencies, amplitude, and phases. When analyzing an amplifier, a frequency spectrum is typically divided into the three distinct bands. So like I've said before, everything we feel here are all vibrations and are all sine waves. The sum of those sine waves is the Fourier analysis, which is this. So we will check the frequency bands, frequency spectrum into three distinct bands. Low frequency range. This is the low frequency range. The region where coupling and bypass capacitors use voltage gain to drop because their capacitive reactance increases at lower frequencies. Mid-frequency range. The operating band where the gain remains constant. This is the gain. The y-coordinate axis is the gain. Here, external capacitors act as short circuits and internal transistor capacitance act as open circuits. The next, high frequency range. The region where the internal parasitic wiring capacitance of the transistor begin to short the signal to ground, causing the voltage gain to drop off. So let's talk about the bandwidth. The range of frequencies, because the x-axis is frequency, the range of frequencies over which amplifier operates effectively from here to here is called the bandwidth. Bandwidth is strictly bounded by frequency FL and the upper cutoff frequency FH. This is the FH. This is a FL. Cutoff low, cutoff high. These cutoff points, also known as the half power or negative 3 dB frequencies, mark the exact locations where the output drops to 50% of its midband value, which corresponds to the voltage gain dropping to 70% of maximum gain. Mathematically, bandwidth is calculated as BW equals FH minus FL. An amplifier with a wide bandwidth can faithfully amplify a broad range of frequencies without attenuating and the signal critical components of the input signal. So if the signal is lower the cutoff frequency here, it will be attenuated. If it's too higher than the cutoff frequency of the high frequency region, it will be attenuated. Everything that is within the frequent bandwidth, that will be given gain. So like I said, if we zoom up close to this part, the negative 3 dB, that will be the low cutoff frequency. We move a slider here as the gain goes lower here at negative 3 dB. That will be the cutoff frequency here. Next. So let's talk about the DC frequency response of a BJT. Effect of coupling and bypass capacitors, low frequency response to lower cutoff frequency. When evaluating an amplifier frequency response, we look at why the voltage gain drops outside the midband. At low frequencies, this drop-off is given entirely by network's external capacitor, capacitor, and one more capacitor here. In DC analysis, we treat these capacitors as open circuits. In mid-band AC analysis, we treat them as short circuits. However, at very low frequencies, their capacitive reactance rises significantly. Reactance is Xc equals to 1 over 2 pi Fc. Because the frequency F in the denominator is small, the reactance becomes large enough that the capacitor no longer act as short circuits. Instead, they drop to significant AC voltage across themselves. Effect of coupling and bypass capacitors. So each of these capacitors affect the low frequency performance in a distinct way. What does coupling capacitor do? This capacitor sit in series with signal path at the input and output, one more capacitor here. As the reactance increases at low frequencies, they form voltage dividers with circuit's internal impedance. This attenuates the AC signal before it can reach the transistor base or the output load. Then bypass capacitors. This capacitor is placed in parallel with the emitter or source resistor to ground. At midband, it shorts the resistor out to maximize gain. At low frequencies, its high reactance prevents it from completely bypassing the resistor. This introduces AC negative feedback, which drastically reduces overall voltage of the amplifier. So each capacitor creates in its own low frequency network, RC network, resulting in three distinct lower cutoff frequencies. One for the input coupling circuit, one for the output coupling circuit, one for the bypass circuit. The mathematical formula for each cutoff frequency follows a standard high-pass filter relationship. The actual lower cutoff frequency, FL, of the entire amplifier is determined by the highest of these individual frequencies. At this specific point, the total power drops to 50%. So as I've said, since there will be three capacitors here, input, output, there should be another capacitor here, and the bypass capacitor will show a different cutoff frequencies in the graph. So which of these cutoff frequency should we use? Which one? So the one we will use is the highest cutoff frequency. The highest of the three individual cutoff frequency. At this specific point, the highest cutoff frequency, the total output power drops to 50% of the mid-band value, marking the exact lower boundary of the amplifier's usable bandwidth. This, okay. So these are all the significant formulas when solving for BJT and JFET frequency responses of electronic devices and circuits in frequency response. So let's try to solve one problem. DC frequency response. Determine the cutoff frequency for the network of figure 9.25 using the following parameters. These are all the parameters. Okay. So first, we apply formula. Beta RE. Beta RE is equal to, beta is equal to 100 times 2 kilo ohms for RE. Then we will get 100 kilo ohms. Next. So we will get the VB. Since this is a voltage divider, we will apply the previous formula, VCC times R2 over R1 plus R2. Then we will get 4 volts. We apply the values and we will get 4 volts. Then we will get then we will get the RE. We will get the IE. So apply the formula, then the RE. Apply the formula, then we'll get the beta RE. Apply the formula, and we'll get the AV, which is negative 90. So now for the actual frequency response, basically we apply the beta RE 1.76 kilo ohms, and apply it in our formula for the FLS, for the CS, for the capacitor at the source, CS. So we apply the formula Ri is equal to parallel of R1, R2, and beta RE. And then apply the formula 1 over 2 pi. The formula is 1 over 2 pi Ri Rs CS. So we apply the CS from the given, Ri from what we have computed here, and 2 pi. We will get FLS. This is the cutoff frequency for the source. Next, for the formula of coupling capacitance, CC is 1 over 2 pi quantity RO plus RL, then the coupling capacitance. Now, RO is approximately equal to RC. So we apply the values. This will be our value for the cutoff frequency for our output coupling capacitance. Next, CC na ulit. CE. CE, the bypass capacitor here, we compute the RE. RE is equal to parallel of R1 parallel 2 over beta plus RE here. So we apply the formula, apply all these values we have obtained before, then we will get 9.38 ohms. After getting this RE is equal to this. We apply the 1 over 2 pi RC, RE, R for the RE, and then C for the CE. Then we apply the values that we have obtained. Then we'll have the cutoff frequency. Since we have 3 cutoff frequencies here, which one should be used? Like I said before, the cutoff frequency that we will use is the highest of them all. Meaning, the cutoff frequency for this particular circuit is that it is 8.7, 87.13 hertz. Okay. This is the source of all the formulas that we have used. Low frequency, FLS, 1 over 2 pi RC, RS plus RI. Then the other FLC, FLE, RE. We have the RE, formula for RE, and then formula for RS, and the other formulas that we need to use for solving for the frequency response of a BGT. Next, AC, frequency response. So so you'll talk about high frequency effects, internal transistor of capacitance, upper cut of frequency, bandwidth calculation, and body plot interpretation. So while external capacitors limit the low frequency performance, the high frequency response of an amplifier is restricted by entirely different factors. Internal transistors capacitance and stray wiring capacitance. At high frequencies, the external coupling and bypass capacitors remain perfect for AC circuits, short circuits, but these internal parasitic capacitance begin to take effect. So, first we will define what is a capacitor. A capacitor is two conductors sandwiching a non-conductor. So, so where did the CBC, CCE, CBE come from? So since the higher the capacitor, the frequency, this base conductor and the E emitter conductor is separated by a non-conductor, forming a capacitor. Even though there is no literally a specifically uh, capacitor in the circuit, there exists a theoretical invisible capacitor for both for all three terminals for the BJT. And also it will exist at the wiring of base to the ground and collector to the ground and the other capacitors. So it will add up, forming a different cutoff frequency for the high frequency region. Internal resist transistor capacitance while and high frequency effects. These are unwanted capacitors. This lower reactance creates low impedance paths for that shunt the AC signal directly to the ground, attenuating the input and output voltages. This is called Miller's theorem. Magnifies this effect. Any capacitance connected between input and output terminals, like the base to collector capacitance, is mathematically multiplied by the voltage gain of the amplifier. This creates a much larger effective input Miller capacitance, which severely restricts high frequency performance. This internal capacitance combined with the circuit's Thevenin resistance to form low-pass RC networks. This results in an input high frequency cutoff and an output high frequency cutoff called HFHO. And for the high FHI. The overall upper cutoff frequency of the amplifier is determined by the lowest of these high frequency cutoffs. So it's the opposite for the low frequency cutoff. If the low frequency, you will get the highest frequency. But for the cutoff frequency for the high frequency region, we will get the lowest frequency of the cutoff for the high frequency region. Once both FL and FH are established, the total bandwidth of the system is calculated directly. For wideband application, FL is often small enough that the wideband is approximately equal to FH. Body plot. To visualize this entire frequency range, we use body plot, which graphs the amplifier's voltage gain in decibels against frequency on a logarithmic scale. So this is called the body plot. When interpreting the body plot, the midband gain from flat as the frequency passes the lower or upper cut of frequency. The gain drops by exactly 3 dB from the midband maximum, marking the half-powered thresholds. Beyond these cut-off frequencies, the gain rolls off a constant rate, typically negative 20 dB per decade or 6 dB per octave for a single pole RC network. If multiple capacitive networks engage at higher frequencies, the slope steepens to 40 dB per decade or more, showing how exactly aggressive the circuit attenuates at high frequency signals. So we will use the same formula as I showed you before, these to solve this frequencies. Determine the network cutoff frequency for the network 3 point figure 3.9.37 using the following parameters. These are the parameters for this circuit. So for the FET, AC response, frequency response, we simply apply the formula. 1 over R sig plus Ri. R sig is 10 kilo. Ri Ri is 1 mega. Multiplied by Cg. Cg is 0.01 microfarads. Then goes the same for here. Cc, capacitance, coupling capacitance for the output. FLC, 1 over 2 pi Ro plus RL quantity Cc. We just applied the Cc. Cc for 0.5 microfarads. Ro for 4.7 kilo ohms plus RL 2.2 kilo ohms and the CC 0.5. Then for the CS capacitor at the CS capacitor at the CS, REQ is equal to RS slash parallel 1 over GM. So we compute. This will be our equivalent resistance 333.33. Then we apply it REQ and the capacitance 2 microfarads. Then you will get the 3 cutoff frequencies. So Which one should we use? The highest cutoff frequency. Since this is a lower cutoff frequency, so we will pick the highest cutoff frequency. So, summary of frequency response. These are the summaries of the frequency response. Power to which the base must be brought to obtain the same number. And then, yeah, comparison between the levels. This is self-explanatory. Lastly, we will talk about operational amplifiers or op-amp. First, let's introduce operational amplifier. What is an op-amp? Operational amplifiers or op-amp is a high-gain DC coupled differential voltage amplifier. It takes the voltage difference between its two input terminals, multiplies it by a massive gain factor, and outputs the resulting signal. To analyze op-amp circuits effectively, we compare a practical real-world IC to an ideal mathematical model. Ideal op-amp characteristics. Open loop gain is equal to infinite. Bandwidth, infinite. Input impedance, infinite. But the practical is only 5 raised to 10. Bandwidth is 10 to 100 hertz. 1 mega. Are the differences of the ideal and practical op-amp characteristics. Then CMRR, common mode rejection ratio, should be infinite. However, in the practical, there is only 10 to 100 dB. The output voltage depends on the VD. However, in the practical op-amp, depends slightly on average input VC, common mode signals. So, to conclude, an ideal op-amp characteristic should be infinite open loop voltage gain, infinite output impedance. So it draws zero input current, and zero input impedance. It also possesses infinite bandwidth and perfect thermal stability. However, in the practical op-amp characteristic, real devices like the characteristic 74 IC have infinite limitations. The open loop gain is very high but finite. Infinite impedance is large but limited. Output impedance is small but non-zero. And bandwidth is limited by internal compensation capacitor. When an op-amp is configured with negative feedback loop, meaning a portion of the output is fed back into the inverting input, if wire is going back into the input, it operates linearly. Under these conditions, you apply two fundamental assumptions to analyze the circuit. The input current is zero because input impedance is exceptionally high. No current flows into either the inverting or non-inverting terminals. The virtual short concept. The op-amp will dynamically drive its output to keep differential input voltage at zero. Therefore, the voltage at inverting terminal equals the voltage at the non-inverting terminal. Basic op-amp configurations. Let's talk about basic op-amp configurations. By rearranging external resistors around the op-amp using negative feedback, we alter closed-loop gain and circuit behavior. First, the inverting amplifier. The input signal is fed through a resistor to the inverting input. The non-inverting input is grounded. The output is amplified and inverted by 180 phase, negated by the gain formula. AV is equal to negative RF over Rin. RF Rin. So what I've just said right now is that non-inverting amplifier, the input, this is like the inverting amplifier, but the input is inputted at the negative terminal of the amp. For the non-inverting, the input is fed at the positive side of the op-amp. The input signal is directly non-inverting input. The output is in phase with the input, and the gain is always greater than or equal to 1. Next, the voltage follower. A special case of non-inverting amplifier where the output is tied back to the inverting input. RF is equal to 0. It provides a voltage gain exactly unity. AV is equal to 1, acting as a buffer due to its high input impedance and low output impedance. Then the summing amplifier. Multiple input channels are connected via separate resistors, resistor 1, resistor 2, resistor N. The circuit into the inverting node. The circuit scales adds the input voltage together into a single combined output signal. Lastly, the differential amplifier. Inputs are applied simultaneously to both the inverting and non-inverting terminals. The circuit amplifies only the voltage difference between the two inputs while rejecting any voltage common to both. Applications of op-amp. Beyond basic amplification, op-amps can perform mathematical calculus and signal processing. For integrator, by replacing the feedback resistor with a capacitor, the input voltage becomes proportional to the integral of the input voltage over time. For example, a constant DC input produces a linear ramp voltage at the output. Differentiator, by placing a comparator at the input and the resistor in the feedback loop, the output voltage becomes proportional to the time of rate of change of the input voltage. A ramp will yield a constant DC level at the output. Lastly, comparator. Operating in open loop without any feedback, the op-amp compares the voltages at its two inputs. If non-inverting input is slightly even higher than inverting input, the output immediately saturates to the positive supply rail. If lower, it drops to the negative rail. So let's try to solve a problem with op amp. So problem solving, calculate the output voltage VO in the circuit here. So if you isolate this part, this is basically a inverting amplifier. And then this one looks like voltage follower. This is just a voltage follower. So how do you apply this? We applied each and individual formulas. So we apply VO is equal to 1 plus 400, which is the feedback of this first op amp over 20, the resistor to the ground, times by 0.1 volts, which is the input voltage. So we will multiply this into 100 over 20. 100 over 20. That is the formula of the summing operational amplifier, plus negative 100 over 10 times 0.1 volts. Then we will simply type this in our calculator. Then we will get the VO is equal to negative 11.5. That is all for this this presentation talking about BJT and AC, BJT, FET for both AC and DC analysis, frequency responses of AC and DC, and finally operational amplifiers. Thank you for watching. Have a great day.